Hello, class. All right, so this morning my internet was just completely out, and it kind of comes and goes now, but class is starting fairly soon. And I also got an email from CLC. You can check those on my phone, and CLC is apparently having issues as well. So thought it would be better to just pre-record today's class and post that. I'll just put it in the, I'll put it in a module for, like the exam module, since what we're doing today is reviewing for the exam. So today we're going to be reviewing chapter 8, which is on rotations. All right, so to start out with, we define position, like angular position. So if we have a rotating object, now picture a wheel or a disc that's rotating, and we can draw a reference line. Say our rotating object, the origin is at the center of this rotating object, and we can define theta as the angular position of this object. And so if the object rotates, say from here at time t equals 0, and then this reference line rotates to here in a time delta t, say delta theta is the angular displacement. So we have theta to describe like the angular position, delta theta is the angular angular displacement. If we divide delta theta by delta t, that's like how much we rotated divided by the time it took to make that rotation. That's angular velocity. And if the angular velocity is changing, we have an angular acceleration. So we define angular velocity and angular acceleration. It's kind of similar to how we define linear velocity and acceleration. Now, they have the same issue that we had in those cases where to do it properly, you have to take the limit that delta t goes to 0. So like this would be the average values over that time interval delta t. So we can't do limits in this class, but we can restrict ourselves to a special case that we can solve exactly. And that is if we have a constant angular acceleration. And in that case, I'm just going to write down the result. So if we know the initial position and initial angular velocity of the object, we can describe its position and angular velocity at all later times. And again, those equations are valid as long as the angular acceleration remains constant. So this is like rotational kinematics, just like chapter 2 kinematics for linear motion. And we can also combine these two and eliminate time to get that equation that relates those variables without time being involved. So let me find an example of a rotational kinematics problem. You can go over. Let's see. That's a very simple one, but maybe we'll do two. So it's, this might even be obsolete by now, but a CD has a playing time of 74 minutes. When the music starts, the CD is rotating at an angular speed of 480 revolutions per minute. At the end of the music, the CD is rotating at 210. Revolutions per minute. Find the magnitude of the angular acceleration of the CD. Express your answer in radians per second squared. So this is mainly, I'm going to get rid of this. It's kind of mainly a conversion issue here. We want to find the angular acceleration, so we can use this second equation. Oh yeah, the time, it's 74 minutes. So here, I should have put it up here initially. So we just have to be careful about units here. Okay, so yeah, let's just use that second equation and solve for alpha, the angular acceleration. That's what the question's asking for. So we subtract omega naught from both sides. So we have alpha t is omega minus omega naught. And if we divide by t, all right, so let's plug it in. Omega minus omega naught, we have 270 revolutions per minute. And then we divide by 74 minutes. It's kind of interesting to think like why this would be happening, like why would it slow down at all? And I think the reason, if it works kind of like a record does maybe, you know, like all the information is stored on the CD and it's rotating. So like different parts of the music are stored on different parts of the CD. And it looks like initially the information is stored on the kind of inner part. And so, or wait, let me actually think about, yeah, like if it was spinning at a constant rate, like if you're looking at the outer, if the information is stored here on the outer part, it's going to go through like a smaller distance, or I'm sorry, greater distance in some time interval. So yeah, let's look at it rotates through a certain angle from here to here. So if you're reading data here, you're getting a lot of data. If you're reading data here, you're getting a much smaller amount. And so I'm not sure how they exactly arrange the information on the CD, but this could definitely be a problem. And so I'm guessing that, you know, it starts out going very quickly. So yeah, I think they store the, like it starts reading near the center, and so it rotates more quickly, and then as you get farther away, it slows itself down. So that, you know, if you lower the time interval, it's a smaller angle, but the greater distance from the center means you can get like the same amount of information. And it's probably more complicated than that, but I think that's the basic idea why it would be slowing down over the course of, you know, playing this music. It goes through the entire CD. But anyways, let's actually answer the question they were asking. So this raises this, you know, another thing we need to talk about. They want the answer in radians per second squared. So remember, one revolution is 2 pi radians, or 360 degrees. And let's convert to radians. So 2 pi radians is 1 revolution. And if we look at our units now, if we cancel out revolutions, we have radians per minute squared. So let's get rid of that. Let's convert minutes to seconds. So 1 minute is 60 seconds. And we square it. So let's check our units, even though, well here, let's just cross it off. We have a minute squared. That cancels off those two. Revolutions canceled out. So we have radians per second squared. So we have 270 times 2 pi divided by 74 times 60 squared. That would be radians per second squared. Yeah. I'll just do this real quickly. 270 times 2 pi divided by 74. Okay, so what I'm getting is 0.0064. Radians per second squared. Now, actually it starts out going 480, ends up at 210. So actually alpha is negative. It's slowing, slowing down. So, yeah, I was kind of careless in the beginning. We have omega minus omega naught. That's negative. So there should have been negative signs in front of everything. So that's the angular acceleration. Not very much, but over the course of 74 minutes, that is significant. Okay, so that was a very straightforward problem. Just the only thing you have to watch out for in that one is units. So let's see if I can find a somewhat less straightforward. I don't think I did this one in class, but it's kind of an interesting one. Let me hold up the picture because a picture will do a better job than I can in drawing. So we have this device here with a motor that's rotating a shaft that has these 2 discs on it, and we're shooting a bullet through them. So let me read the problem. I'm going to try to draw this. We have these 2 discs that are rotating together, and we shoot a bullet. Okay, so let me read the problem. Okay, so the drawing shows a device that can be used to measure the speed of a bullet. The device consists of 2 rotating discs separated by a distance of 85 centimeters. Let's see, and rotating with an angular speed of 95 radians per second. The bullet first passes through the left disc and then through the right one. It's found that the angular displacement between the 2 bullet holes is 0.24 radians. So the bullet passes through one, and then it has to travel this distance between them, between the 2 discs, and then it hits a second one. You know that that's how much the discs rotated in the time it took for the bullet to pass through. And of course, we're assuming that these discs are made of some kind of flimsy material, so that the bullet can pass through without slowing down significantly. Trying to measure the speed of a bullet, if we slow it down, that's obviously a problem. So, let's see, from this, determine the speed of the bullet. So, let's write down, we assume the bullet's moving at a constant speed, and so the distance that it travels, call that the displacement, well here, that's d. We're given that. Say it's moving with an initial velocity v naught, which is what we are trying to find. And if we say like t equals 0 here, and then t equals delta t, so I guess I'll call that delta t, then we know that it rotated through that angle, and it's moving at a constant rate of 95 radians per second. So we can use, well, basically this equation with alpha equals 0. So we have delta theta is omega naught delta t. You can also look at that just directly from the definition of omega, delta theta over delta t. And so we just have to put this stuff together to get velocity. So one way we could do this, let's actually just divide the two equations. So we have d divided by delta theta is equal to v naught divided by omega naught. So like we have v naught delta t over omega naught delta t, but that gets rid of the delta t, and so we can pretty directly solve for the velocity of the bullet. So we have omega naught d divided by delta theta, and let's plug this in. So omega naught, we have 95 radians per second. And again, always be careful about units, particularly in these rotational problems, because we use both radians, degrees, or revolutions. And sometimes, some of the equations are only valid if you're in radians. So always pay attention to units, but be a little bit extra careful in this topic, circular motion. Okay, and this will give us centimeters per second. Let's convert to meters. So 1 meter is 100 centimeters. So now we have the velocity in meters per second. We can simplify this a little bit. We have 95 times 85 divided by 24. 95, so like 0.24 times 100, 24. So let's just do that, see if we get something reasonable. Looks like it should be good. Yeah, 336 meters per second. Okay, so yeah, let's move on from kinematics. We're going to talk about this S equals R theta. So let me just write that down. So let's go back to our rotating disk. So let's say our disk is rotating at a particular angular velocity omega, which may or may not be constant. And let's look at a point on the disk that is at a distance r from the center. So this point is moving around in a circular motion, it has a tangential velocity. And that tangential velocity is given by r omega. Now that was derived, I mean we can find this velocity very easily. We go through in a time equal to 1 period. We've got 2 pi r over t, and or actually, we can just do distance over time, but we want to relate that to omega. So the angular velocity would be 2 pi radians in 1 period. So capital T is the period. That's how long it takes to complete that circular motion. And so V is, just distance over time. And 2 pi over T is omega. And we're using radians here. So, because the distance that we complete 1 rotation, we wrote that in terms of radians. And so like all of these equations depend on, they're only valid if we are using radians. So let's make another note of that. Radians only. And it's unfortunate that they're written this way because, I still think we should write like S equals R theta over radians. Then the equation would be valid no matter what you plug in. Like if you plug in radians, like you plug in 3 radians and you divide by a radian, theta would just be 3. If you plug in something in degrees, then you can put a conversion factor in there. And it's not a big deal if you're using these equations directly. But often they're used to derive other things. And so sometimes when you're plugging in units, you'll like get an extra radian in there, or you're missing a radian or something, and you just have to throw it in there. So you just have to recognize that it's kind of implied that the units are radians. Actually, let me redraw this. So we look at this point at a distance r, and it has a tangential velocity that depends on both the distance from the center of rotation and also on the angular velocity. So if the angular velocity is changing, that means the tangential velocity is changing, which means we have a tangential acceleration, and that is given by r alpha. So this the relation between the linear, the tangential values and the angular values, that's very important. In particular, if we're looking at a rolling disk. So I'd say this is a rolling disk. So it'd be moving this way. And in this case, to describe the motion of a rolling object, the motion is actually fairly complicated. Like if you look at this point here, if the disk was just spinning, it's moving in a circle, but in reality it's going something like this, because the disk is moving as well. And so it's called like a cycloid, that shape that it's actually going through. And so it's actually a complicated thing to describe the motion of a point on this wheel, like relative to an observer that sees it rolling by. But the center of the disk just moves horizontally as the disk is rolling. So to describe the motion of the disk, we just, let's say VC, and we describe the motion of just that the center of the disk. That just has a velocity, it just moves horizontally, much easier to deal with that. And for a rolling without slipping, which is pretty much all we talk about, the velocity of the center with respect to the ground is equal to the tangential velocity of a point on the edge of the disk. So rolling without slipping. The velocity of the center with respect to the ground is equal to that tangential velocity of a point on the edge of a disk, which is r omega. And it has to be because, like, the disk overall is moving to the left, but if you just look at the, like, say this point that's in contact with the ground, the rotation, the velocity of this point, let's call that point A, it's rotating this way, so the velocity of A relative to the ground is to the left, and the velocity of the center with respect to the ground, the velocity of A relative to the center is to the left, and the velocity of the center with respect to the ground, so I usually draw it the other way. This is to the right, this one is to the left, and the velocity of point A relative to the ground is 0. So let's say this is our positive direction because that's the way it's moving. Then we'd have VCG minus VAC has to equal, well here, let's use our relative motion subscripts. So the velocity of A relative to the ground is velocity of A relative to the center plus velocity of the center relative to the ground. Those are vectors. And now let's just call this our positive direction. Everything is in a line, so we can just focus on magnitudes. This is equal to 0. So the velocity of A relative to the C is negative, let's say minus the magnitude VAC. The velocity of the center with respect to the ground is positive. And so we can see that these two have to be equal in magnitude, which is what wrote there. So that's rolling without slipping. And similarly, like the distance that the wheel travels is equal to, like the displacement is just r delta theta. And so we have, like rolling objects are very important. So we have these conditions for rolling without slipping. And if it's rolling and slipping, like if the road conditions aren't good, like icy or something, and your tires are just spinning without you moving very far, that's, we don't really do anything with that. Just, we would certainly need more information to describe something like that. So let me find a problem for like a rolling type of problem. So let's see. Here's a kind of straightforward one, but let me read the problem. So in 9.5 seconds, a fisherman winds 2.6 meters of fishing line onto a reel whose radius is 3 centimeters. So we have this fishing line, and so it takes 9.5 seconds. Let's call this L. The length of the line is 2.6 meters. And the radius of the reel is 3 centimeters. So the question is, we're doing this at a constant speed. So what is the angular speed of the wheel? And again, this is that kind of like rolling without slipping condition. So like if the wheel makes one rotation, the amount of line it's picking up is equal to that circumference, or 2 pi r. So we have this V equals R omega. So it's not really rolling, but same kind of condition. There's no relative motion between like the fishing line and the edge of the disc. Okay, so we want to find omega. So we can say that omega is equal to, we've got the tangential velocity divided by the radius. So we're using that equation. And the tangential velocity, that's just the length of the line divided by the time. So we have L over R delta T. Now, this will give us an answer in radians per second. If we take care of the other units like meters and centimeters. So yeah, we're using this equation, so radians are implied. It's not going to show up when we plug in the values because of the way we write the equation, but it's implied here. So let's plug it in. So yeah, just the speed, if you look at this point, say at the bottom, it traveled a distance L in the time t. So the velocity of that point is L over delta t, and omega is V over R. So now let's just plug it in. So we have L is 2.6 meters divided by R, which is 3 centimeters. Let's fix that right away. 100 centimeters per meter. And then we divide by delta t, which is 9.5 seconds. And let's just throw in a radian, because it's implied. So here we have, 2.6 times 100, we have 260 radians, divided by 28.5 seconds. Centimeters and meters cancel out, and so that's that ratio L over R is dimensionless, and let's plug that in. So it's about 9.1 radians per second. So that's how fast this wheel, or this reel, is spinning. It's a constant speed, just to lift up that fishing line. So that's that relation between the linear and tangential variables. Let's see if we can find another one. Rolling motion, that might be good. Do this. So say you're riding a stationary exercise bicycle, and the electronic meter indicates that the wheel is rotating 9.1 radians per second. Let's see. Kind of doubt that they would use radians per second as a unit, but apparently they do. All right. So the wheel has a radius of 45 centimeters. So if you ride the bike for 35 minutes, how far would you have gone if this bike was actually moving? And so basically we're the distance that you would travel is equal to the radius of the wheel times the angle through which that wheel rotated. So delta x is equal to r delta theta. We know r. Make these two consistent. So we know r. We have to find delta theta, the angular displacement. And it's constant. So we can use this equation, just ignoring that last term involving alpha. So theta minus theta naught is the angular displacement. So delta theta is omega naught times t. So if we put these together, delta x is r omega naught t. So let's plug this in. So r is 45 centimeters. Omega naught is 9.1 radians per second. And t is 35 minutes. Now, again, remember this is based on, ultimately on that equation. It's kind of the same thing almost. And so this radian is implied. So here we're getting a displacement. We shouldn't have any angular units ultimately. So let's just erase this radian. Okay, and now it's a matter of dealing with the units. Let's convert at least to meters. So a meter is 100 centimeters, and 1 minute is 60 seconds. So now we'll get our distance. Kind of running out of room here. Let's just cross off the units. I don't like doing that unless I know it's going to work. Makes it hard to fix otherwise. But now we have our distance in meters. So delta x, we have 45, 9.1 times 35 times 60 divided by 100. Maybe we want to convert to kilometers, actually. If you're on a bike for 35 minutes, why don't we do that? 1 kilometer is 1,000 meters. Hopefully you've gone at least a kilometer in this time. Actually, I don't think so. Let's just leave it in meters. I don't seem to have gone very far. Let's see numerically. 45 times 9.1 times 35 times 60. And then divided by 100. Oh yeah. So this would be 8,600 meters. Or, here, let's just put it here. .5 kilometers. So that's, fairly reasonable. Yeah, that's how far you would have gone on the bike if you were actually moving. All right. So I'm going to do one more problem. And I'm going to start by actually holding up the picture. It's kind of hard for me to draw this for some reason, but it's that windmill right here. So let me read the problem. Let me attempt to draw this. Well, let me read the problem. Okay, so the drawing shows a golf ball passing through a windmill and a miniature golf course. The windmill has 8 blades and rotates at an angular speed of 1.25 radians per second. The opening between successive blades is equal to the width of a blade. So I don't want to use the letter W for width because that might be confused with omega. So let's just call that L. The width is L, so width of the blade, width of the opening is also L. A golf ball with a diameter of 4.5 times 10 to the minus 2 meters, or 4.5 centimeters, just passes by one of the rotating blades. What must be the minimum speed of the ball so not be hit by the next blade? So like the ball, like if it enters this gap, I mean obviously if it hits a blade it's going to stop. If it hits this gap, it kind of depends on where it enters the gap as well. So like if you have the blades looking like this, it's like if the golf ball enters here, it has its best chance because this one is swinging here. Or if it enters in the middle, you know, this one it'll hit it sooner. So we can assume kind of like the best case scenario here. It's going to enter here, and it has to pass through this gap before the next blade hits it. So we want to find the minimum speed that the ball has to be going. So next time you're at a mini golf course and you come across this, you know what to do. So very practical problem here. Okay, so let's first look at this picture, which I did not completely draw. But we have, we have 8 blades, and there's 8 gaps between them in total. And so we can look at going all the way around. Let's call delta theta this angle here. And so there's 8 blades and 8 gaps. So overall we can say that 16 delta theta is equal to 2 pi. There would be 16 all the way around. So delta theta, or we can divide by 2. So 8 delta theta is equal to pi. Okay, so I'm going to do a few things here. One is, I'm not sure if it's even an approximation. I don't want to really go through it. It'd be kind of difficult to see if this is an approximation or not. But, yeah, you look at the ball as it's crossing, like the blades are in a plane. And so if you look at the ball when it's crossing that plane, initially it's a dot, and then it grows to its maximum radius, and then it shrinks back down to a dot. So if all you're looking at is a cross-section going through this plane, so like when the blades pass through, they're going to, like the point is, let's say the ball is at maximum diameter. So that means the ball's like half in the plane, half is on each side of the plane. And as it continues, say it's coming out of the board and the blades are swinging, say this way, because it's coming out of the board, this cross-section is decreasing, and so it can kind of get away of the blade as it's coming towards it. So the point is, we can assume that that we can kind of disregard the width of the ball when considering like the rotation of the blades. Because normally if the diameter was significant, the blade would have to rotate through a smaller angle than delta theta in order to hit the ball. So I'm assuming that because this cross section is going to keep shrinking as it passes through, that by the time the blade hits it, it'll be gone. But it has to pass through this gap fast enough. So I hope that point makes sense, that we're going to look at the rotation of the blade. We're going to see how long it takes to go through that angle delta theta. And we can disregard the diameter of the ball in this case. That is an assumption. We could be more careful and, because if the ball is at its maximum diameter in this plane, when the blade hits it, well then, then it's going too slow. So we can assume it's already kind of, if the ball enters here, so say here's one blade, here's the next blade. And so maybe the diameter, we're not even given the length of these blades. So we don't know how big this gap is compared to the diameter of the ball. So let's say that it, actually no, it would probably enter, it's drawn like this. So let's say the blade rotates through this angle, it's going to hit the ball, but in the time it rotated through that angle, the ball has gone more into the board, and so its cross-section is constantly shrinking as the blade is moving closer to it. And so, I think we can just disregard the diameter of the ball here. We'll assume that it's moving fast enough that it shrinks so that this cross-section is shrinking. That gives it some extra time. And I think we have to make that assumption because we're not given the length of the blades. Problem does not give us that, so we kind of have to make this assumption. So anyways, let's kind of put a couple things together. One thing that we need to do, though, let's look at the time it takes for the blades to go through this angle delta theta. So delta theta would be omega delta t. So delta t is the time it takes for the blade, say this point, to move over to this point. That's delta t. Oh wait, no, let's redefine that. Here, we already used the fact that the length is the same. Yeah, let's define delta t to be this time interval, from here to here. Yeah, because once the blade goes from here to here, it can hit the ball. We don't have to look at, So just like the leading edge of the blade to cross that gap. We'll define delta t that way. And now if we look at, say this is the plane that the blades are rotating in, and here's the ball that's moving with a velocity v, which is unknown, we know it has that time interval, delta t, to cross this plane. And so we can also say that v, or the distance, it has to travel a distance equal to its diameter in that time interval, delta t. And so let's kind of put all of these things together. We want to solve for v. So again, I think we can do this little trick where we just divide these two equations. Let's do this. Let's say v delta t divided by omega delta t. V delta t is d, and then we're dividing, omega delta t is delta theta, so the delta t's cancel out. So v over omega is d over delta theta. And yeah, I think we can put all this together now. So the velocity here, we have omega d over delta theta. Now, this is a situation where, yeah, we use this. I think we might have an extra radian show up that we're going to neglect because, yeah, we use like V is equal to R delta theta. Yeah, so we're going to just neglect that radian. It's that problem that keeps coming up. So here, omega, we have 1.25. Oh no, we're actually, let's write it. Yeah, we didn't actually use those equations that depend on radians. We're going to divide by delta theta. Oh, yeah, what is delta theta? Delta theta is pi radians over 8. So we have to throw that in there as well. So let's put all this together now. So we have omega times d, which is given. I'm going to write that as 4.5 meters over 100. And then we're dividing by delta theta, which is pi radians over 8. So we'll put the 8 on top. And then it'll give us our velocity in meters per second. So let's calculate that. 1.25 times 4.5 times 8, and then divided by 100 pi. Now, when you divide by 100 pi, you have to be very careful. You can't just say divided by 100 pi and hit enter, because it'll divide by 100 and then multiply by pi. So you have to either use parentheses, or what I did is I just said divided by 100, enter, and then divide by pi. So anyways, what I'm getting for the velocity is 0.14 meters per second. Okay, so that's how fast, that's a minimum speed of the ball, assuming that you time it right. And yeah, so just kind of a fun problem to do. So we'll leave the review at that. And yeah, sorry, these internet issues, I thought it'd be better just to pre-record this because I got an email from, like mine is going in and out. But I know CLC sent an email that they're having problems. And so I don't trust Zoom right now. And even if it worked for me, it might not work for you. So pre-recording in this case, I think the way to go. But yeah, we'll assume everything we fix tomorrow. Be a normal class tomorrow, where we will review chapter 9.